Okay, good morning. So let us continue the lesson. So if you remember, we started learning about how to multiply matrices, and then we realized that one important property is lost, and that is commutativity. So in general, there is no guarantee that if I have two matrices A and B, A times B is equal to B times A. Sometimes it is even not possible. Yes. So let me just try to continue. So today, that is a good remark. I want you to know that is, by the way, very important. If I have two diagonal matrices, yes, if I have two diagonal matrices of the same order, then if I want to multiply these diagonal matrices, multiplication is extremely simple. So it means that what I need to do, I need to take the first entry on the main diagonal of the first one multiplied by the first entry on the main diagonal of the second, and put it on the first entry on the main diagonal of the result. And then you continue this process until you end. So multiplication of matrices in usual is not a very interesting thing to do, especially if the order of matrices are big. But when it comes to diagonal matrices, it's actually extremely simple. So this is a very, very important class of matrices that working with them is extremely simple when it comes to multiplication. Let us, by the way, explore this a little bit. So what do I mean here? If I have two diagonal matrices, so let us just try to test this idea. And of course, you should be able to prove it rigorously using the main definition, the sigma notation definition of the entries of the product matrices. So it means that, for example, if I have, let us consider 3 by 3. So if I have a diagonal matrix like this is a diagonal matrix of order 3. Let us multiply it by another diagonal matrix of order 3. So D 0, 0, 0, 0, E, 0, E, 0, yes, and then 0, 0, F. So you just do your work. So what we are supposed to do you remember? I need to partition the left-hand side matrix into rows in my head and the right-hand side matrix into columns. And then I start multiplying each row by each column according to the rule we learned last time. So what was the rule? For example, first of all, is it possible? Let's just review a little bit. This is a 3 by 3. This is also 3 by 3. Is this product defined? Yes, because these two numbers in between are the same. And then what will be the result at the end? The result will also be a 3 by 3 matrix, yes? So if you want to multiply them, so you need to partition the left-hand side matrix into rows, the right-hand side matrix into columns, and take each row and multiply it by each column, by each and every column of the other one. So for example, I take this one and I multiply it here. Then I put it as the first row and first column, because this is first row and this is first column. How I am supposed to do this? I have to multiply the first one by the first one, which is AD, multiply the second one by the second one, which is 0, multiply the third one by the third one, which is 0, and then remember them and add them. And the result becomes AD, and then I put it here. So that was the rule we learned, yes? And then you continue. For example, you take the first row and then multiply it by the second column. You are supposed to write the answer here, the first row, second column. Yes? So how should I do that? Again, the same story. I take the first one, multiply it by the first one, which is 0. Take the second one, multiply it by the second one, which is again 0. Take the third one, multiply it by the third one, becomes 0, and I add them, and then resulting number is actually 0. Yes? And then you can just do this yourself. So if you take this one, multiply it here, it becomes 0. For example, if I take this one, multiply it here, it becomes 0. But if I take this one and multiply it here, it is not 0. What will happen? 0 will be multiplied by 0, B will be multiplied by E, and 0 will be multiplied by 0. And I am supposed to add them. And then you see that the result is BE. And in this way, you can convince yourself if you continue, here we will get CF. Okay, so but as soon as you realize that I have two diagonal matrices, the multiplication is extremely simple. So what you need to do is just take A multiplied by D, take B multiplied by E, and take C multiplied by F. Okay, now the question, because I told you that when we say that commutativity is lost, it doesn't mean that you cannot cook up some examples in which A times B is equal to B times A. So whenever we have classes of matrices that are commuting, it is good to remember them. For example, a big class of commuting matrices are these diagonal matrices. Do you agree? Because if I interchange them and multiply them, what will happen? The result will be dA, EB, and FC, but these are just numbers, so that would be the same. So when it comes to multiplying diagonal matrices, I don't need to be careful about the order in which I multiply them, yes? Okay. Another thing that I want to talk about is this remark, so let us just go here. So this, first of all, a piece of notation. So if I have a matrix m by n, when I use this, I mean the ith row of matrix A. So this capital R is sitting for row. This index I means which row I am interested in. And this is my matrix that I am taking the ith row from. So if I have a generic matrix m by n, when I write this, I mean this row matrix. Do you recognize this is the ith row of this matrix? Because if you see, the row index is always I, and the column index starts from 1 to up to n, which is the number of columns of this matrix. And then another piece of notation I will use is this one. So this is the jth column of matrix A. So it means that I go to my matrix A, find the jth column and take it out and put it as a column matrix. So these two pieces of notations I want you to know, because there will be an important remark here. I want to explain the content of this remark for you. Even though, because sometimes the product itself is not important for us, might be we are just interested in one element of the product, or sometimes we are interested in one row of the product or one column of the product. So it is important to know these rules, okay? So for example, I just want you to, because I want you to also improve your skills in reading mathematics. So here, A is an m by n matrix, B is an n by p matrix. So by this, I am guaranteeing you that A times B is definable, yes, because n and n are the same. So what will be the result? M times m by p, yes. Now assume that I and j are integers, so that I lies between 1 and m, and j lies between 1 and p, because as you told me, the resultant matrix is m by p. Now this tells you, how do you read this? Can you interpret this in words? Because this, I really want you to improve your skills in this course. So because most of the time you don't have some person to teach you, you need to read the articles or books and try to understand what is written there yourself. So how do you interpret this result by words? Number one. Yes, Rocco?
Sure. So I would read it as the matrix AB is equal to the row.
No. You just read what is the meaning of this. This is not matrix AB.
No.
So this square brackets. If I don't put this in square brackets, because
any random any entry.
Not any entry. Yes, the ijth entry.
Okay.
Yes, because you see I and j, I have fixed them. When I write this, it means I fix I and j, but in a way that I satisfies these conditions and j satisfies these conditions. Yes, and for that chosen I and j, if you ask me what is the ijth entry of the product AB, what can I do? One way, of course, is to multiply the matrix, and after that go and read the ijth entry of the product. But this tells you that you don't need to find the whole product. What you need to do is
Can multiply the ith row with the jth column.
no, not good. Just be very clear. You have to be very precise. You have to take the ith row of A multiplied by jth column of B. Not just saying taking ith row and multiplied by the jth column. Yes, you have to be, because what this means, it means the ijth entry of the product AB is equal to the ith row of matrix A multiplied by the jth column of matrix B. And it is extremely important. You cannot just be random here. So you have to take the ith row from the matrix on the left and multiply it by the jth column of the matrix on the right. So this gives you only one entry of the product. For some reason, sometimes you don't care about the whole product, you just care about one entry. So that would be a faster way. Okay, another person. Can another person translate this into English? That piece of notation, I am using it here. So for example, can you tell me what is the meaning of this piece of notation when I introduce that above? What is the meaning of R sub A times B? Yes?
It's the ith row of the matrix A times
A
B.
times B. So it means that if I am interested in the ith row of the product AB, just one row, then it is better to do it in this way. Now, can you interpret this yourself? Yeah?
The ith row of A times B.
Times the whole B, yes? The entirety of B, yes? And this interpretation now becomes clear. Now, sometimes you are interested in one column, a particular column of the product. So if you want to find the jth column of AB, be careful. You take the whole A and then just multiply it by the jth column of B. Yes? It's important, by the way, from theoretical point of view to understand what is going on. Might be this is the most interesting one, and which is not actually trivial. So what does it mean? It means, can you interpret it? Because I want you to understand how to feel the mathematical formulas. So this is why I really want you, whenever I write recommendations, I ask you to read the text, because it's important, yes?
The matrix A times B is equal to the sigma from N to K.
Yeah.
Of
No, just read it yourself and try to explain it in words as if you are the teacher.
Okay.
So can you understand the mechanism this formula is talking to you?
Kind of.
Yes, okay, so just explain it. By looking at this formula, this tells you something. Okay, what is that message?
You take the K.
So if you want, you need to start something like this. If you want to multiply A from left to B, then
Okay, if you want to multiply
yes,
A to B,
yeah,
then you take the sigma from N to K, from K to N, and take the kth column of A and multiply that by the kth row of B to find
no,
y.
yeah.
And then you continue and increase the value of the sigma until you reach until K equals to N.
It's good, but not very convincing. Can someone else make it better? Because Gustav actually started. It was good. But I don't want you to say sigmas and things like that. Because sigma is a notation in mathematics we use. Yes? What do you say?
Maybe you multiply all the columns of A with the corresponding rows of B.
That corresponding word is crucial here. Yes, thank you. And then?
And then you add them all up.
Add them all up. This is the best way to read this formula. Because if you say sigma, sigma is something we know in mathematics community that means sum. But sum is more natural word. So this means that if you want to multiply A by B, A from left to B to the right, then one alternative is to take one column at a time from the matrix A and multiply it by the corresponding row of matrix B, by the way, what will happen? It becomes one number or it becomes a matrix?
One number.
Be careful.
It becomes matrix.
Because if that is a number, then the sum of a lot of numbers becomes a number on the right. But on the left, you are supposed to have a matrix. So this means that this is the first time you see, most of the time when you talk about rows and columns, rows are on the left, columns are on the right. Yes? But here, this is different. This is the first time that the column comes first and the row comes second. Okay, I want to describe these first, and then we go to the next two. Okay, so for example, let us consider these two matrices. Okay, so let us just switch back. I want to write these matrices on the board and try to understand what is going on. Okay, so the matrices that we have here, we want to understand the content of that remark. So the matrices that I just told you, it is A, 1, 2, 3, 4, and then B is 5, 6, 7, 8, 9, 10. Okay, so for example, if you want to calculate A times B, entry number, for example, here I have written 2, 3. By the way, if I ask you to calculate AB, you can calculate AB and answer all these questions right away. Okay, that is not the purpose of this example. The purpose of this example is understand this remark better. So if I ask you really to multiply that, by the way, the orders are so simple that you can immediately do that, yes? So this is 5, 6, 7, 8, 9, 10. Is it doable? Let us check. This is 2 by 2, this is 2 by 3. So what is the result? These two are the same, so this multiplication is possible, but the result will be a 2 by 3 matrix. Yes? Okay. Now, I partition it to rows, I partition it to columns in my head, and I start multiplying each row by each column. Be careful. Now, a row is on the left, a column is on the right, so if you multiply, it becomes a number. But the last formula we talked about, the column comes first, the row comes second. Okay, so we will talk about that. So let us just do it in our head. So what's the answer? What's the first entry? Can you do it? Let us say 1 times 5, keep it in your head. 2 times 8 is 16, and that 5, 21. So that is 21. What is the next one? 6 and 18 is 24. And then 7 and 10, 27. Yes, and then here 15 and 32, 47. And this is 18 and 36, 54. And this is 21 and this is 61. Yes. So by the way, I just intentionally wrote an example that you can really do it very fast. So it is not time consuming at all. So if I immediately ask you this question, you can immediately answer. What's the number? The one sitting on the second row, third column. Second row, third column is 61. Yes? But this tells you that instead of doing it like this, if you are interested in only this entry, you don't need to do it in that way. What to do? You need to take the second row of A and just multiply it by this third column of B. I just want you to understand what's the meaning of these things, okay? So what is the second row of A? Written in row form, yes? This is the second row. And then I multiply it by the third column of B, which is 7 and 10. So then the answer becomes what? This is, by the way, 1 by 2. This is 2 by 1. So it is possible, and the answer becomes 1 by 1, which is a number. So this is just 21 plus this, which is 61. But be careful. What do you get at the end? You don't get a matrix at the end. You get a number at the end, because this is just one particular entry of the product. Yes? This was the content of the first part of that remark. The second part was understanding this formula. R, I, AB. Ith row of the product is ith row of the matrix on the left multiplied by the whole matrix B. Yes? So that was, I want you to understand this formula by calculating the third row of the AB. You already know the answer because you have the AB in its entirety. So if I ask you what is the third row of AB, by the way, that is a mistake. That's the second row. There is no third row, yes? There is no third row here. So if I ask you what is the second row, what do you get? Immediately you write 47, 54, 61. So you already know the answer. But this tells you that if you want to do it, there is an alternative way. These are important from theoretical point of view. Okay, so what does it mean? It means that if I want to calculate this, I take the second row of A and multiply it by the whole B. What does it mean? It means the second row of A is 3 and 4, and I just multiply it by the whole B. 5, 6, 7, and I have 8, 9, 10. Okay, so this is 1 by 2. This is 2 by 3. Is it doable? Yes, because the 2's are the same. And then I have to write it as matrix 1 by 3. So, but there is one row. You have to take this row and multiply it on each one of these columns. By the way, it's not that hard to understand that this is really true. Yes, so I do the same thing. So this becomes 15, 32, 47. And then 18 plus 36, 54, and then finally 61. And that is what you actually expect. So I want you to understand the content. So if you don't mind, I will skip the other one because that's very similar. I thought we can do that. What was the other one? If I am interested in the jth column of the product, then I take the whole A, but I don't need to multiply it into the whole of B. What I need to do is just take the jth column of B and multiply it. For example, if I am interested in calculating the second column of the product AB, what I do, I will take the whole A. The whole A is this matrix 1, 2, 3, 4. And then I multiply just by the second column of matrix B. Second column matrix B is 6 and 9. Yes? Okay, and then you know that. Is it possible to do it? Definitely yes, because this is 2 by 2, this is 2 by 1. So the result will also be 2 by 1. Yes, but I partition it into rows, take each row and multiply it by that column. So this becomes 6 plus 18, 24, and then becomes 18 plus 36, 54. And then you see that this is exactly the second column of the product matrix. Okay, but understanding the other one is also important. So the other one tells you that if you want to find matrix AB, there is another alternative way to do it. And that is writing AB, the whole AB as a sum. By the way, be careful. You might say we already had this formula. No. What we had before, do you remember? So let me just remind you about these. If A is m by n, B is what? N by P, yes? And then what is the product? The product is M by P, yes? For example, if I take I from 1 to M somewhere, an integer, and J from 1 to P somewhere, an integer, then I am allowed to ask you what is AB, IJ, yes? We answered this question in a little bit different way today, here. But the definition was a sigma. Do you remember? The definition was sigma of, do you remember how to write it? I would write little a and little b. I put a counter for my sigma, which always starts from 1, but goes up to which index?
N.
N, a common value between them. And then this a starts with I index, b ends with j index, but I need an index here, another index here, which is the counter of the sigma. So that was the way that we wrote it. But be careful, this is a sigma, but it does not generate the whole matrix. It generates only one single entry, which is ijth entry of my sigma. But here, this is the whole matrix. The whole matrix is equal to sigma. K goes from 1 up to, I will come back to that, and then I will take the kth column of matrix A multiplied by yes, the kth row of matrix B. Okay, can you tell me K goes from where to where? Still the dimensions of my matrices are this. Can you tell me what is the number on top?
Is it n?
It is n again, yes, because how many columns are there in A? The number of columns is n. Or if I ask you how many rows are there for B, you say again n. So this goes from n. I want you to understand the real difference between these two formulas. This formula generates the whole matrix at the end, but this generates just one single entry of the matrix at the end. Okay, let us try to understand this formula. Okay, so if I want to calculate A times B, I myself always use this standard way of multiplying, but it's important to understand that multiplication can be viewed in a different way as well, like this. Let us just do the calculation like this, okay? For example, in our case, what is n? In our case, n is 2. So let me calculate this right-hand side. So the right-hand side is sigma, k goes from 1 to 2, and then I will have ck of A, rk of B, plus, that is, and I expand that. When I expand it, I mean that I choose k equals to 1, so this becomes c1a r1b, and then plus c2a r2b. Okay, but if I ask you what is the first column of A, this is your matrix A, this is your matrix A, the first column is this matrix. So you have to write it in column 4. So this becomes 1, 3. And then you multiply it by the first row of B. The first row of B written in matrix 4 is 5, 6, 7. Plus the second row of A, which is 2, 4, multiplied by the second row of B, which is 8, 9, 10. Yes? So this is called row column decomposition, or column row decomposition, CR, decomposition of AB. So this tells you that if you multiply these two matrices and these two matrices and add the result, you will get the whole matrix AB. Okay, let us check that. I told you that this is important from theoretical points of view. So we will come to some applications of this way of doing it. I myself never do it. If I want to multiply two matrices, I just do it the normal way. But it is important to see that there is an alternative to do that. Okay, but can you tell me how should I multiply these two matrices? Are they even possible to multiply? Yes, because this is what? This is 2 by 1. This is 1 by 3. Is it doable?
Yes.
Yes, because ones are the same. And then what do I get? I get a matrix which is 2 by 3. Okay? So how? I need to decompose the left-hand side to rows and the right-hand side to columns. And then I start multiplying each row by every column here. But there are only one single entries in each one of them. So I multiply the first row by the first column. So 1 times 5 is 5, nothing else, so I have to write 5. And hopefully you understand what's going on. So take this one, multiply it here, it becomes 6. Take that one, multiply it here, it becomes 7. And then I go to the next one. Hopefully you agree with me. It is 15 and 18 and 21. And I do the same thing for this next product, which is also doable. So this becomes 16, 18, 20, and then it becomes 32 and 36 and 40. Now, if I add these two matrices, it becomes exactly the matrix that we expect. It becomes 21, 24, 27, 57, 47, and then 54 and 61. Yes? Is that right? Yes. So this is important to know. This is called column row decomposition of the product. So that was the content of this remark. Is that clear? Okay, now if I switch back, there are two more items here. The next one is not that important. Usually this doesn't appear that much in linear algebra, but this is extremely important because a lot of times we want to multiply a matrix into a column matrix. This appears a lot. Okay, so now this tells you that if you want to do this, by the way, can you interpret this again yourself? So what is the English content? What is the conceptual content of this formula? What does this tell you? It tells you that if you have a matrix, for some reason you are interested to multiply this matrix A from the left to a column matrix, then of course you can always do it usual way, but rather than that, an alternative way is to think it in this way. What to do? What is X? What are these X's?
Values of the column.
Exactly. So this is important to understand. This is very good, by the way, to understand. This X that appears here is exactly these X's that appear here, okay? So this means that take one of them, any one of them, and multiply it by the corresponding column of matrix A, okay? And then start adding all these matrices together, then it becomes this product, yes? And then you can interpret it more or less the same thing here. For the row matrices. If you want to have a row matrix on the left and you want to multiply it by a matrix A, then what you need to do, take each one of these entries from the row matrix and multiply it to the corresponding row of A and add them up. Yes, that's the idea that you want to do. For example, here, if I go back to the board. So it means that if you want to take this matrix, for example, let me just take matrix B, 5, 6, 7, 8, 9, 10. If I want to multiply it by, I don't know, let me make it simple, 1 and 2. One way is just normally multiply it, but another way to see it is to do what? Take this one, yes, the first one, and multiply it by the first column, yes, and then plus take the second one and multiply it by the second. By the way, this is not possible, sorry, because that product is not doable, yes, because this is 2 by 3, so I have to give you a 3 by 1 matrix. So let me write 1, 2, and 3. Okay, so I will take the first one and multiply it by the first column, which I wrote it wrong again, and then plus I take the second one, multiply it by the second column, and then I will take the third one and multiply it by the third column. If I calculate this sum, it would be exactly equal if I calculate this in the normal way. Okay, so if I calculate this sum, let us just do it. So I multiply 1 here, so it becomes 5, 8. I multiply 2 there, it becomes 12, 18. I multiply 3 in, it becomes 21 and 30. And if you add these three matrices, let me write here, 5, 12 is 17, and this is 38. And then this is 26 and 56. That is the answer that I get. But if I want to do it usual way, I partition it is to the rows, to rows, and then multiply each row there. Okay, and then hopefully you understand that this will be the same thing, yes? Yes. Okay, so let me just do it. This multiplied by that, what's the answer? 5 times 1, keep it in mind. 6 times 2 is 12, and 7 times 3 is 21. And if I add them up, it becomes what? 38. And then I will do the same thing here. 8 times 1, I keep it in mind. 9 times 2, keep it in mind, and 30. And then add them up, which becomes 56. So you see, if you just do it normal way, you will get the answer. It is important to understand that there are different ways to answer the same question from theoretical point of view. Okay. So now this lesson is actually very important to understand, this coming lesson here. Matrix algebra and number algebra. So I want to compare them. So it's extremely important to understand the differences and have it in mind when you are working with matrices. So you see, what are the differences? The first thing we learned is we lost commutativity, yes? Okay, if A and B are numbers, A times B and B times A are always defined and equal. In other words, the multiplication of numbers is commutative. Still, as we saw in the previous examples, if A and B are matrices, it might be the case that AB and BA or both are not defined. And even if AB and BA are both defined, still they might not be equal. This is the content we learned before. Okay. Therefore, the matrix multiplication is not commutative. Not respecting this vital difference between the algebra of numbers and the algebra of matrices gives rise to confusion as we progress in the theory of matrices, so make sure that you understand and appreciate it. Notice that when we say that matrix multiplication is not commutative, it does not mean that one cannot come up with examples of matrices A and B such that AB is equal to BA. For example, I try to just do some trial and error, and I come up with these matrices. For example, if you are patient enough, you can calculate it yourself. You multiply A by B into B from the left and BA. They happen to be the same. Okay? I actually really want you to read the text and try to do these things yourself. It is very simple. So when we say it is not commutative, it means that there is no guarantee that AB is equal to BA, but sometimes we can have this situation that AB becomes equal to BA. By the way, I intentionally avoid 0 because you might say that, okay, if I have 0 there, then I can guess that they might be the same. But you see that even I do not have any zeros there, but still A times B is equal to B times A. This is important. In other words, if A and B are given matrices, you are not allowed to presuppose that AB is equal to BA. Okay, this is the important thing. You can write AB equals to BA only if in the problem that you are investigating, it is given directly as an extra piece of information regarding matrices A and B, or you can demonstrate it indirectly from the information given in the problem at hand. This motivates the following definitions. Do you understand? So you are not allowed to just blindly write A, B, B, A unless it is given in the problem itself, or you have some idea why this is going to work here in this case. And this word I want you to learn, commuting matrices, this is also a terminology. So if A and B are matrices so that coincidentally AB is equal to BA, then we say that A and B is a pair of commuting matrices. Yes. For example, the previous example, I can say A and B are commuting. Yes. This is the terminology we use. Okay. By the way, show that if matrices A and B are commuting matrices, then they are square matrices of the same order. So you shouldn't be able to, don't look for rectangular matrices to be commuting. They cannot be commuting. If there is a chance that you can find commuting matrices, you should look for them among square matrices of the same order. Okay, why? This is my question for you. Yes?
Isn't it possible to have two rectangular matrices all being the was it identity matrix only with ones?
No. Only so identity matrices, be careful. Those are classes of square matrices.
Okay.
We do not have any identity matrix when it comes to, because identity, do you remember upper triangular matrices?
Yeah.
And lower triangular, they are square matrices. After that, we learned about diagonal matrices, which are a particular form of triangular matrices. And then after that, we learned scalar matrices.
Right.
And after that, we learned identity matrices. So all these group of matrices are always square matrices.
Isn't it still possible to have two rectangle matrices all with the value of 1?
Yes.
And then being commutative?
Yeah, that problem claims no. And I want to say no. So this tells you that if you want to have a chance to find commuting matrices, do not look for them among rectangular matrices. It is not possible. Okay? We want to understand why. So the point is this. My question for you is this. This question is telling you that if someone tells you that A and B are commuting matrices, then you can yourself understand that these two matrices have to be square matrices, and they have to be square matrices of the same order. Why is that? It's not hard at all. Just think about it. For example, let me start. Let us go for a contradiction if we can find. So, for example, assume that A is m by n, and B is p by q. For example. But you are telling me that A and B are commuting. What does it mean? It means that you are telling me that AB is equal to BA. When you say that these matrices are commuting, it means AB is a matrix which is equal to the matrix BA. But this is, first of all, because AB should be defined, this means N has to be equal to P. If N is not equal to P, A times B is not defined in the first place. But BA should also be defined. Yes? So what does it mean? It means B on the left, A on the right should be doable. So this means what? If B times A is doable, it means what?
M equals Q?
Q is equal to M, yes.
Okay.
Okay? But still, there is no guarantee that all these numbers should be the same. Why all of them should be the same? Because AB is defined, N should be equal to P definitely. Because BA is defined, M should be equal to Q definitely. But I am claiming more. I am claiming that all these four numbers are equal. Why? Yes?
If they weren't equal, they wouldn't be of the same sizes.
At the end.
Yes.
Because you know that when I say this matrix is equal to this matrix, it means that the order of this at the end is equal to the order of this at the end. Okay, what is the order of this at the end? Because n is p, it is doable to multiply them, but what will be the order at the end? It will be m by q. Yes? Yes? And then what will be the order of BA at the end? If you put B on the left and A on the right, we'll realize that these has to be the same. And what will be the order at the end?
P by M?
P by M. P by N. Yes?
Yeah.
Okay, and now you are telling me that these two matrices are equal. So what does it mean? It means M should be P and N should be Q. Yes? So this means that all these four numbers are equal. So this means that they are square matrices of the same order. Yeah, is that clear? Yes or no? Yeah, it was very simple. So don't look among rectangular matrices for if you want to find an example of commuting matrices. Yes?
Can you prove that it doesn't work with rectangular matrices?
No, we proved that. That's the proof.
Okay.
Because I am assuming that I have a commuting pair, and I prove that they have to be square matrices of the same order.
Okay.
So it means that there is no alternative for that. Yes. Is that clear? Okay, so let us see. This is a very simple exercise, by the way, but I want to wait for you, okay? So let me switch the view and go here and wait a little bit for you here. So, by the way, so this is an important remark I want you to remember. So that's the one big class of commuting matrices. So whenever you want to think about a group of commuting matrices, think about diagonal matrices. We just realized that. Okay, so consider this example. Okay, I want you to do these two examples, 1.79 and 1.80. And if you don't mind, so I need to learn the shortcuts. How can I pause OBS? Do you know, Robert? Yeah, okay. Okay. But anyway, is there any way without switching back to OBS being able to pause that? Okay, let me just do it myself. Okay. Okay, did it work? So here you see I have given you a pair of square matrices of order 2, and I'm asking you, if possible, fine-tune these A and B so that capital A and capital B are commuting. This is just a terminology I want you to understand. By reading the question, you realize that my goal is to fine-tune A and B so that the product AB turns out to be equal to BA, which of course is not always true. We want to fine-tune A and B so that this happens. So what I am supposed to do, I have to calculate AB, which is 1, 2, minus 2, 1, multiplied by 2, 3, A and B. And then if I multiply them, this row by that column, what is that? 2 plus 2A. And then this multiplied by that is 3 plus 2B. And then I go here minus 4 plus A. And then I go here minus 6 plus B. Yes, is that understandable? So I just multiplied them. And I multiply them the other way around. 2, 3, AB first. And then 1, 2, minus 2, 1 second. And I do the matrix multiplication. This time I have to divide this into rows and this into columns. So this multiplied by that, it becomes 2 minus 6 is minus 4. And then 2 times 2, 4, plus 3 is 7. And then A minus 2B. And then 2A plus B. Do you have any problems in multiplication here? Yes. Can you confirm my calculations? Okay. Now I want to fine-tune A and B so that AB is equal to BA. Be careful, this is an overdetermined problem, yes? So you have to respect all of them, not just finding A and B and leave it. Because in principle, how many unknowns are there? 2. How many equations I need? I need 2, okay? But how many equations I have? 4. So be careful, you have to satisfy all 4 of them, even though if you just use 2 of them, you are in principle able to find A and B, okay? So what happens, this is important, if AB is supposed to be equal to BA, then this means that I am facing an equation, a system of 4 equations, but in 2 unknowns. So the equations are 2 plus 2A is minus 4, and then 3 plus 2B is 7, and then minus 4 plus A should be A minus 2B, and then 2A minus 6 plus B should be 2A plus B. Yes? Of course, it is clear that these two are enough to find A and B, but it doesn't mean that I solve the problem if I don't check the last 2. Okay, so from here, what is A? I move it to the right, it becomes minus 6, A becomes negative 3. And from here, what is B? It's 2. Yes, so you see that with these two I am done, but it is not guaranteed yet that the other two equalities are also satisfied, which is important, by the way. I have to check them. What happens if one of them or two of them are not actually satisfied? What will be the answer to this problem? Yes?
Undefined.
Not undefined. So you need to have respect for the grammar. Yes? So that's not undefined. How do you say the answer then? Yes, Robert?
A and B and A are you can't find A and B
They are commute. So it is not possible to fine tune A and B so that AB is equal to BA. Okay, so that is not undefined or something. You have to express it in that way. Okay, but let us check. Is it correct or not? Yeah, it is correct. Yes.
Yes.
Yeah, if you can check -3, put it here, it becomes -7. If I put -3 here and 2 here, it becomes -3, -4 is -7. So that is confirmed. We can also easily confirm that this is also true. So because all of them are satisfied, so the answer will be A equals to -3 and B equals to 2 only. So it means that if you just take any other numbers except these two, then they will not be commuting. That is clear from here. Okay? Okay, the next lesson, I just asked you to multiply A and B. Okay? And then hopefully you did it correctly and you got the answer. Let me just do it here. Do you have any questions here? Okay, so if I multiply AB, so it is 1, 2, 2, 4. I have asked you to confirm that this becomes 0. By 0, what do I mean? Here, I want to confirm this. Hopefully you understand that this is the 0 matrix because the product is a 2 by 2 matrix, so this 0 is the 0 2 by 2 matrix, yes? So is it correct or not? Let us check. I partition this to rows and this to columns. 1 times 4, keep it in mind, it is 4. 2 times -2 is -4. Add them, 0. Take this one and that one. 1 times -6 is -6. 2 times 3 is 6. If you add them, it becomes 0 again. And then take this one and multiply it here. 8 minus 8 is 0 again. And -12 plus 12, 0 again. And that is the 0 matrix. Okay? But the reason that I brought this up is because of the content of the next remark. Okay, so let me just remind you what we are doing right away. Right, the title was comparing the matrix algebra and number algebra. Okay, so why do you think what is the message of this example to you? Because I want you to understand what are the deviations from normal algebra. Yes. So can you compare this? What is the message of this example, which will be the content of the next remark in the lecture notes? Yes?
Maybe the product of two non-zero matrices can be equal to 0.
Yes, can you compare it with something like that in numbers?
In regular numbers, one of the numbers needs to be equal to 0.
And that is called the zero product rule. Okay, so it means that if A and B are numbers, yes, we have used this a lot, yes, and you know the product is 0, what is the conclusion that you can draw?
One of them is 0.
At least, yes, A is 0 or B is 0. This is no longer true in matrix theory. So if the product of two matrices is the 0 matrix, there is no guarantee that one of them at least has to be equal to the 0 matrix. And I have actually intentionally made this example in a way that you don't see even one 0 entry. Okay, no 0 entries are there. So this is the second message, the deviation between matrix algebra and number algebra. The first one that we lose commutativity. The second one is that the 0 product rule is not guaranteed when it comes to matrix multiplication. Is that clear? Okay, so let us go now here. So that is the content. As we know, the real numbers enjoy the so-called property of the 0 product rule. This is the name I usually refer to it. That is, if A and B are real numbers such that AB is 0, then either A is 0 or B is 0. However, as the previous example shows, the matrix algebra does not respect the zero product rule. In this example, none of the matrices A and B is the zero matrix, but still their product AB is the zero matrix. So that is the second deviation. The first deviation was we lose commutativity. The second deviation is that we lose the zero product rule. Okay, and I want you really to do this one and read the message, because this will give you a message for the third remark. Okay, just do that one for number 182. Yeah, just try to confirm that. These are simple calculations, but yeah, every mathematician actually have done simple calculation at least once in his or her life. And you have to do it, okay? The important thing is that after doing the calculation, read the message from this example, which will be the content of the next remark, and that is the third deviation from number algebra, and these are the only ones. Okay? Just a moment, please. Okay, could you confirm that these are equal? So I think this is a very simple calculation. Let me just do it here on the board easily. So A times B is 1, 2, 2, 4 multiplied by 2, 1, 3, 2. So what's the answer? This is 2 plus 6 is 8.
Yes.
And this is 1 plus 4 is 5. And this is 4 plus 12 is 16. And that is 2 plus 8 is 10, yes? Hopefully done right. And then I go to AC. So I multiply 1, 2, 2, 4 by C. Minus 2, 7, 5, minus 1. So this becomes minus 2 plus 10, again 8. This becomes 7 minus 2, again 5. Minus 4 plus 20 is 16. And then 14 minus 4 is 10. So it confirms that they are equal. But what is this is not important because this was very simple. But what is the message? Yes?
In regular numbers, B equals AC would imply that B equals C. However, it's not true for matrices.
Not true. Yes. That is also the third message. It's extremely important. Do you remember? We had this. But of course, there also in numbers, we have to be a little bit careful. So if I tell you that A and B and C are just numbers, and if I tell you that A times B is equal to A times C, you can, in principle, most of the time, why do I say most of the time? You can conclude that B is equal to C. You can cancel A from both sides, but by one condition. What that condition is?
If A equals 0.
If A is not equal to 0. This is called multiplicative cancellation. So it means that if the product AB is equal to AC, and if you know that this number, which is common in this is a common factor, is not 0, you can simply just get rid of them and conclude that these two numbers has to be the same. This is different in algebra, in matrix algebra, as you see this in this example. I have given you 3 matrices, and I have respected that this matrix is not the 0 matrix. Even I didn't put even one single entry there, okay? And I see that at the end, AB and AC are the same matrices without B and C being equal. Yes. They even don't share even one single entry, let alone to be equal. So that is the third important thing that you shouldn't blindly use because you have used to use it in numbers, okay? So this means that multiplicative cancellation in the algebra of matrices in general is not true, but we will fix it later, okay? And then we will change this condition. Something similar to this condition will be later. We will discover what will be that condition so that this cancellation is possible. But for the time being, there should be some thing that you have to check before being able to do it. But generally, it is not true. Just by looking at this matrix, which is not the 0 matrix, you are not allowed to cancel A from both sides and conclude that, okay? So this means that if I have matrices AB equals to AC, even if I know that this matrix is not the 0 matrix, if I conclude, this is also conclusion, if I conclude B is equal to C, this is in matrix theory wrong. We will fix this condition to another condition so that then this will be true. Okay, but for the time being, no, it is not true. Okay, so let me back to the notes again. So here I have written, let me just read it once more to check if I have written everything correctly. So we know that in the real numbers, multiplicative cancellation is allowed. That is, if a, b, and c are real numbers such that ab is equal to ac and a is not equal to 0, we can cancel a from both sides of the equality and conclude b is equal to c. However, as the previous example shows, multiplicative cancellation is no longer allowed when dealing with matrix multiplication. Therefore, if ab is equal to ac, for matrices A, B, and C, we cannot cancel A from both sides of this equality and conclude B is equal to C, even if A is not equal to the 0 matrix. This is still another difference between the algebra of real numbers and the algebra of matrices. However, we see later that if the matrix A is invertible, we will talk about that hopefully in this course, a property we will study later, then multiplicative cancellation is valid. To get a taste of this situation, check the following example below. So here, for example, by the way, that is also important. But before doing this example, let me read the summary. So that is important. The product of every pair of real numbers is always defined, whereas this is not the case for matrices. As we learned, for a b to be defined, the number of columns of A has to be equal to the number of columns, the number of rows of B. In multiplying two real numbers, the order that we multiply these numbers is irrelevant, but we have to pay close attention to the order we multiply matrices. The final answer might be different depending on the order we multiply two or more matrices. Matrix multiplication does not obey the zero product rule. The multiplicative cancellation is in general not valid in matrix algebra. So this you need to understand that. But before actually leaving this lesson, let me see. I will stop here. But this is one of the examples because I can look a little bit ahead of myself. And now I have given you an example for which cancellation is allowed, without saying how did I come up with this example. So this is a matrix A. I want you to show me that if I have this matrix as A, then suddenly cancellation becomes valid. Yes? But I don't know, is it a good example to put it here? I don't want to confuse you. I want you to understand in general cancellation, multiplicative cancellation is not allowed, but sometimes it is allowed. Because I can look ahead into myself, I was able to come up with an example with that property that the cancellation is allowed. But I think it would be a good exercise at the moment to show, without knowing that part of the lesson, that if I give you this matrix, then the cancellation suddenly becomes allowed. Still, you see this matrix doesn't have any zero entries. In my example, this didn't have any zero entries. In that case, it was not allowed, but in this case, suddenly becomes allowed. Then we will see why this is the case. So I will stop here, and I want you to work on it now. So show me that if A is this, even if I haven't given you B and C, but you just know that B and C are a square matrix of order 2, this cancellation is allowed. So that is the content of this exercise. And I want to wait for you for 10 minutes, and then I will actually solve it, and then we end up the lesson today. And hopefully you see that I have put the lecture notes on, so I'm updating it regularly. So I'm adding exercises and things like that. Try to come up with me. Yes?
I don't understand the question really.
The question is this, in the previous example, I showed that AB equals to AC was not a good reason to conclude that B is C. Yes?
Yeah.
But in this example, I am asking you, if A is this matrix, not the matrix in the previous example, and if I tell you that A times B is equal to A times C, then definitely B has to be equal to C in this case.
Are we supposed to choose values for B and C?
That is the content of the question.
Okay.
So I need to, because that is a little bit hard from calculational point of view, but you shouldn't choose numbers.
No.
Yes?
Matrix.
A matrix.
Yeah.
But you just put letters instead of entries. And you have to prove it algebraically, not for a particular, if you just randomly write a B and a C and then it will work. But then the question is that why it works for another pair. So you have to do it systematically, yes?
Okay.
Yeah. Just a moment. Okay, so the example is this. We have this matrix A, which is 1, 2, 3, 4, yes? My claim is that if A times a matrix B, which is of order 2, square of order 2, is equal to this, I want to prove that for this particular matrix, this is allowed. Yes, I want to prove this. So what can I do? I would say that, okay, let me take any matrix B, for example, A, B, C, D, and is equal to A times any matrix C, for example, E, F, G, H, yes? So I would say that, okay, B is a 2 by 2 matrix. This is the general form of a 2 by 2 matrix, and C is also a 2 by 2 matrix. That's the general form. Now you are telling me that this product is equal to this product. I want to confirm that this matrix is really equal to this matrix in this case.
Why did you put A?
What?
Why did you put A?
Here?
Yeah.
No, because A times B is equal to A times C.
Okay.
I am assuming that this is my B.
Yeah.
I'm assuming that this is my C.
Okay.
And I am asking, you have given me that AB is equal to AC, so I'm allowed to write this, yes?
Yeah.
And from here, I want to conclude that this matrix, even though I don't know any one of them, it becomes equal to this matrix, even if I don't know any of them. Yes, that's the whole point of the exercise.
Yeah.
Yes? Okay, so what should I do? Instead of A, I put 1, 2, 3, 4. And instead of B, I just put a generic matrix here. And I say that, okay, you are telling me that this product is equal to this product. Yes? So then let us see what can I conclude. I can conclude that if I do the multiplication here, 1A plus 2C, then 1B plus 2D, 3A plus 4C, and then 3B plus 4D. Yes? This is supposed to be equal. If I multiply this here, this becomes E plus 2G, and F plus 2H, and then 3E plus 4G, and then 3F plus 4H. Yes? Do you confirm that? Okay, and then if this matrix is equal to this matrix, then what can I conclude? I can conclude that A plus 2C is equal to E plus 2G, and then I will also write 3A plus 4C is equal to what? 3A plus 4G. Yes? And I also have B plus 2D is equal to F plus 2H, and then I have 3B plus 4D is equal to 3F plus 4H. So do you agree? So I multiply this matrix and that matrix, I equate them, I get these 4 equations. But I want to confirm that A is equal to E, B is equal to F, C is equal to G, and D is equal to H. If I can show that, then I am done. Yes, can I do that, by the way? Yes or no? I want to confirm that A has to be equal to E. So what I do, for example, I do one of them. I multiply this by 2, minus 2, so it becomes minus 2A minus 4C minus 2E minus 4G. Yes? And then I add this to this equation. Minus 2A plus 3A becomes positive A. Minus 4C plus 4C are gone. Minus 2E plus 3E becomes E. Minus 4G plus G is just this. So I confirm that A has to be equal to E. Yes? And then you can do it step by step yourself. For example, here, for example, I can multiply this by minus 2. So it's minus 2B minus 4D is equal to minus 2F minus 4H. And then add this one to this one. Minus 2B plus 3B is B. Minus 4D plus D is 0. And that is just F. So I confirm that B is also equal to F. Yes? And now look, if B is equal to F, they are cancelled. 2D is equal to 2H, so it means that D is also equal to H. If A is equal to E, E and A are cancelled. 2C is equal to 2G, so it means that C is also equal to G. So this means that this matrix as a whole should be equal to this matrix for this particular matrix. So the bottom line is that for this matrix, the cancellation law is possible, is valid. But for the previous matrix, it was not valid. So in general, it is not valid unless we know what we're exactly doing, yes? And that criterion will come later in the lesson. Any questions? Okay, thank you very much. Yeah, please start reading the lecture notes. If you find any misprints, typos, or whatever, please inform me so that I can fix them. Thank you very much.